In this segment of the lecture, we will talk about another acceleration structure, bounding volume hierarchies. We already discussed the bounding volume test, where you can test a ray against a box. If the ray misses the box, then it also misses all of the geometry or all of the triangles within the box. Intersecting a ray with a box is in many cases a simple coordinate check. We will talk a little bit about the mechanics of this ray-box intersection. Note that there can be intricacies with this test and you do need to consider some edge conditions, but on the whole it is a very simple test. You can also have hierarchical bounding boxes. That is, you can have one bounding box for some of the objects, another bounding box for another part of the objects, and then you can put that together in a larger bounding box. Let's talk a little bit about the math of the 2D bounding box test. Similar kinds of ideas apply in 3D. Remember that we are trying to find the equation of a ray. A ray can in general be written in this form. Where P0 is the original location and P1 is a vector which is the direction vector corresponding to the direction in which the ray propagates. We are interested in finding the t at which the ray intersects the box. We can first consider the intersection with the vertical components of the box that correspond to particular x coordinates for x min and x max. As shown here, you have a t corresponding to x min and a t corresponding to x max. Similarly, you can intersect the horizontal extents of the box, and you can consider a t corresponding to y min and a t corresponding to y max. What are the conditions for the intersection? Of course, t must be greater than 0 for a ray to intersect the box at all, and then t must lie in the range of x min and x max. This t value is where the ray actually intersects the box, and x min and x max correspond to the edges, the sides of the box as shown in the diagram. Similarly, the t value where the ray intersects the box must lie within y min and y max, between ty min and ty max. Now, if you look at the geometry of the situation, you can see that the question is, can we find a t value such that it will lie between tx min and tx max, as well as ty min and ty max? Those correspond to the x and y ranges of intersection. In effect, the value of t must lie between tx min and tx max. It must also lie between ty min and ty max. That means those ranges must intersect for the value of t to actually be valid and intersect with the bounding boxes. There is no intersection if the x and the y ranges do not intersect. As shown here, you have the x min and the x max range which doesn't intersect the y min and the y max range. In this case, there will be no intersection. However, if we moved the y min and the y max range so that it was a region here, then there is this intersection range and you could find a t within it. Therefore, the conditions can be summarized that if tx min is greater than ty max or ty min is greater than tx max, then the ranges do not intersect and you return false. Otherwise, there is a ray bounding box intersection. How do you handle hierarchical bounding boxes? Well, if the ray hits the root box, then you intersect with the left subtree, you intersect with the right subtree, and then you merge the intersections. What does merging the intersections in the context of ray tracing mean? Simply that you find the closer intersection. This can be written recursively as you can go down the entire tree of bounding boxes. Notice that, of course, you need to handle conditions when the bounding boxes overlap. And furthermore, at some level when you reach the leaf nodes, you will have to intersect the actual objects. That is as far as how do you intersect a ray with hierarchical bounding boxes or a bounding volume hierarchy. In developing an acceleration structure, it is important not just to be able to traverse the structure and have a ray that intersects with the structure, but you also need to be able to build up this bounding volume hierarchy from the seed. Here I have given the pseudocode of the function to do that. Given a particular list of objects or an object array A and an axis, which is the x, y, or z axes, n is the length of this list. If there is only one object, then the left tree will be A0, which is the first object, the right subtree will be null, and the bounding box is simply the bounding box of the object A0. Otherwise, if there are two objects, then you simply make the left tree one object 0 and the right tree object 1. The bounding box, you have to have a way of combining the bounding box of A0 and A1, or of the left and the right object. If you have more than two objects passed into this function, then you need to split. You first find the midpoint M of the bounding box of A along the axis that we are given. Based on this midpoint, you partition the geometry. For example, here is my bounding box. I have a bunch of triangles here. I have a midpoint, let's call this M. And I will partition the geometry into this left region and the remaining region, which is the right region. That's what this partition step is doing. You partition it into lists of size k and n minus k around M. And you create the left and right BVH nodes. Notice that because this axis was now split along the vertical axis, when you look at this region or this region, we will now do the next split along the horizontal axis. If you have the bounding boxes for the left and the right branch, then the bounding box for the whole region will simply be given by the combination of the left and right bounding boxes. Because you are doing axis plus 1 mod 3, you also have splits which are evenly distributed along the x, y, and z axes. There is a refinement on this method to create the bounding volume hierarchy, which is known as an area heuristic. Simply, instead of looking at the midpoint of the bounding box, you pick the axis and the location of the split carefully. So you test several possible splitting planes, typically having at least 9 recommended splitting planes across x, y, and z. You choose the best one. And then you have an area heuristic where you're trying to minimize some function which involves the areas and the number of objects. So you combine the areas of the child box and the number of primitives in each, and you try to minimize that. This will take a longer time for construction, but will be a better balanced alternative. This bounding volume hierarchy does speed up ray tracing quite substantially, and I would highly recommend you're not going to be able to go through the rest of the course without having some kind of an acceleration structure. For those of you implementing in optics, the bounding volume hierarchy is built into optics. And in fact, these kinds of fast ray tracing techniques are now a built-in part of ray tracing software and hardware such as optics. So if you're using an existing ray tracer like NVIDIA's optics, you simply need to say, build me a bounding volume hierarchy. And if you're implementing there, you can directly use the optics BBH and you don't have to implement it yourself. Now, if you are interested, you can read more deeply about the surface area heuristics and look at similar methods. And if you actually follow the literature in this area, there's also a question of how do you update the acceleration structure in dynamic scenes when the geometry is changing? How do you make updates quickly for animation so you can have real-time ray tracing of animated scenes?